Have you ever wondered why the sky is blue, or why it changes to red or orange at sunset? Of course you have. It's a question we all ask at some time or another. Well, this question can be answered using the concept of Rayleigh scattering. Rayleigh scattering is the scattering of light by particles without a change in wavelength. It can be described by this really complicated equation here, but the most important variable that affects the intensity or power of the scattered light is the wavelength, because it has the biggest exponent. In order for Rayleigh scattering to occur, the scattering particle must have a radius smaller than 1/10 of the wavelength of the light it is scattering. This means that the gaseous molecules such as oxygen and nitrogen, not the solid particulate matter like dust, are the particles in the atmosphere that scatter light differently based on wavelength. The sun emits pure white light, which is a combination of all of the visible wavelengths, which range from 380 to 700 nanometers. Blue light has a shorter wavelength than red light, so it is scattered more efficiently, and that is why the sky is blue. To further explore Rayleigh scattering, I conducted an experiment using a fluorometer. A fluorometer is a machine that has a light source, in my case a xenon lamp, that sends a beam of light towards a scattering sample, and then the intensity of the light scattered at a 90-degree angle is measured in counts per second, meaning how many photons or light particles hit the sensor every second. The fluorometer allowed me to excite certain wavelengths of light, or in other words select a specific color of light to project, and then measure the intensity of the scattered light at that wavelength. I plotted the raw data I collected in a graph, and then corrected the data using a ratio mathematically calculated by the fluorometer to account for the fact that the lamp did not project the same number of photons at each wavelength because it did not emit pure white light. When wavelength to the -4th power was plotted against the intensity, the graph showed a linear relationship between the two variables, which was expected because of that super complicated equation from before. Now, some weird stuff did happen at the smaller wavelengths due to absorption, but that would take at least another 3-minute video to explain in greater detail. Want to see what Rayleigh scattering looks like on a smaller scale? Grab a glass of water and mix in about a tablespoon of milk, and then head to a dark room in your house with a flashlight. Turn off the lights and shine the flashlight through the glass. Notice how the color of light changes as you get farther from the light source. Also, try experimenting with different ratios of water to milk. This parallels how the composition of the molecules in the atmosphere affect the color of the sky, because different molecules scatter light more or less. This means that Rayleigh scattering can also help us to understand the concentration of certain molecules in the atmosphere, such as dangerous pollutants, based on the color of the sky, which can be measured using a photometer, making this old concept still relevant today.